Good morning, Sydney, and good afternoon, good night to everyone else. Today we are very glad to talk in the Australian Systemic Functional Linguistic Association Conference, and the title of our talk is the Pedagogical Choices in Developing a Supplementary Language-Focused Textbook for First-Year Physics Courses. Today's speakers are Dr. Alfredo Ferreira, who is a lecturer at the Vantage College in the University of British Columbia. And I am Wucheng Zhang, which is a PhD student in the physics department of Princeton University. I did my undergrad in the University of British Columbia, and I've worked with Alfredo for several years. For today's talk, we're gonna overview the pedagogical choices in supplementary physics textbook, and we will introduce problem-solving genres in physics. Then we will talk about semiotic modes in physics and associated competencies. Finally, we will introduce our models of physics problem solving. In the end, we'll invite questions and discussions.
Thanks, Wucheng. I'm going to move ahead now with the pedagogical choices. So this is a one-year funded project funded by the Teaching Language Enhancement Fund of UBC to develop a unit-by-unit supplement for standard first-year physics textbooks. And we're reporting on the first phase of the project, the curriculum aims and the outline and the development of the physics-oriented materials. The progression across the supplementary textbook is determined by the increasingly advanced target physics concepts from the physics textbook. So there are two problems introduced in our units, two physics problems. Especially the first problem is vetted for typical pitfalls in one or the various stages of the solution for first-year students. So the identification, understanding, and practice of mode-linked competencies, especially those competencies linked to novel concepts. Certain concepts that come up in first-year physics might challenge mathematics. Others challenge a qualitative thinking through figures and so forth. So, and thirdly, expanding the scope and depth of the language functions, language being one of the mode-linked competencies. And so we are focusing on two pedagogical genres that are kept constant across the textbook. Keeping them constant allows us to focus on the development of physics concepts and on the linguistic features of the genres. So they are peer discussions among students solving problems and formal written solutions with rationale. And secondly, so progression within the textbook units follows the teaching learning cycle, which I'll describe a little in more detail a little later. So we highlight the functional variation of semiotic modes across the stages of physics solutions. And this involves attention to multimodal competency. We created three fictional student characters that typify mode-related orientations, competencies, weaknesses, and so forth in physics practice, and the mode continuum between spoken and written versions of the same solutions. So we do this to highlight variation, of course, in language and the roles of language in solving physics problems. The project attempts to engage students in novel ways using videos. We gamified some of the units, the tasks in the units, and we also add elements of popular culture in the development of the problems. So we develop our own problems by and large, and without saying it, we drop little hints to popular culture and areas of student interest. Also things like indigenous knowledge that we're seeking to advance here at UBC. Me making in first year physics, of course, involves language, image, and math in combination. And physics instructors and researchers of physics education call this translating representation between modes. and it's critical in solving physics problems. So meaning making in first year physics involves competence in each mode, and here we have the some results from Beichner's research on student interpretation of kinematics graphs that has its own whole set of issues. So math, graphs, language, each one involves mode-specific challenges and affordances, of course. And it also involves, of course, shifting between modes to solve problems. So we focus on these two genres. Student peer group discussion is a key site for learning um, in tertiary context. And the formal written solution, with or without rationale, is a common high stakes genre. About the rationale move, actually within the written solution, our investigations showed that in first year physics at UBC, learners' rationale for their choices in solving physics problems is optional. It's always beneficial. There is a small time cost for students writing rationale, including rationale for their choices. But if the answer is correct, then there is no benefit. But an incorrect solution backed by rationale with effective disciplinary reasoning, then students might get a partial grade for that. And of course, adding rationale also indicates practice self-regulated reasoning. Just before we continue up to here, we have found that our project is getting some attention in the science. So our long-term goal is actually to develop these resources for other science fields, and we've been talking about this for a little while now. And so the chemistry professors at Vantage College have picked up on the idea and have run with it to some extent. So here we see the chemistry professor focusing on chemistry exam problems and then using or developing a script of students solving this problem, also students with particular profile in relation to chemistry literacy and in relation to the particular order or progress of what she calls problem solving practices. Not quite stages, perhaps, but in any case, problem-solving practices that she wants to highlight in chemistry. So this is interesting and very encouraging. We have an opportunity to extend the funding next year, and hopefully we'll do that and move into chemistry and then calculus. Okay, back to physics then. So focusing on the teaching learning cycle. So this is the progression of material within the units of our textbook. Field is built through the physics content course and textbooks, which learners' heads are generally in. But within the supplementary textbook, we focus on what is first year physics teaching and learning at UBC, and then very specifically reading word problems. As for explicit instruction, we focus on the three main modes across solution stages, identification of common mode related orientations of first year physics students. We do this through the scripts that we develop with these students solving problems together. These spoken solutions are analyzed and compared with the written versions. For joint construction, we seek to develop intersemiotic competency and first year physics literacy within the units through reflection on mode length orientations of the three student characters, spoken solving problem in groups. We throw them up, offer new problems, and they vary their roles in relation to how and where they contribute to the solution. Exploration of the speech writing variation using the two versions of each solution, and then joint construction of written solution, joint construction being with peers primarily, and then development of intersemiotic competency supported across the units, guided again by the learning objectives in the content textbook, and the expanding language functions, expanding scope and delicacy of attention to language. And independent construction comes with unit end physics problems where a variety of the mode-related competencies will come into play, and their attention will have been on this multimodal competency. Okay, and of course in the physics content course, assessments, which we hope to be in dialogue with to some extent, but the students certainly would be. Here's a draft of the work plan, and you can see in the first column here, these are the units introduced in the textbook. The first unit, you can see some of our building field, reading word problems, and so forth. The problems we've developed, you can see here, for example, we have developed a physics problem from the red light, green light, which is a game that came up in the very popular TV series Squid Game, Korean TV series. We just throw it in there and hope students, this is from Squid Game. A cool problem that Wucheng developed in any case. So there you see some of the problems. And then here we were experimenting with the order, the progression of language features that we want to focus on, and also explore their multimodal realizations. Here you can see the three characters, Ava, Bang Chao, and Carol. So this kind of just a quick map of how our work is progressing. I also would like to just point out the five-stage approach to solving physics problems taken at UBC Physics with the obligatory elements. I'll just mention that. So from a physics word problem, typically students would then draw out the key elements of the problem. So what's obligatory there is a coherent display of known and unknown elements in play in the problem. Interpreting the problem using a physics model. So here translating elements and relationships in terms of recognized technical models. And now entering into the math, naming, listing equations and methods that have been selected to address and operationalize the physics models, and then solving the math, solving for the unknown values, and then checking and interpreting the solution, so evaluating the solution using alternative methods. And there in the alternative methods, you see the strong focus on translating representation, of seeing the same problem in a different way. So structurally, that multimodal competencies is built into the five-stage approach. Okay, I also wanted to illustrate, these are draft versions of our Doctor Who problem. And you can see there the script for a peer group discussion, where one student here has come to the solution very early, and through their discussion they found that, and see the names are actually even different, but anyway, comes to the solution too early, and we see some recursion happening in the stages as the students go back to a previous stage, realize that the mathematical solution is not the physical solution once the mathematical solution is checked qualitatively and physically. So it is corrected. And then in the formal written version, we have a relatively linear progression. Pointing out here as well some of our early linguistic analysis of comparing spoken and written versions, also earlier draft versions of these solutions. You see some higher nominal density there in the written version. What's interesting here is when we look at this line, so within the model version, we can treat the doctor as a point moving in the planet. So that circumstance of roll guide is a very, very clear modeling of the doctor as in a physics concept, right? So as a moving point. This was so clear when in my discussions with the students that this was enacting theory through language.
Thanks, Alfredo. Now I'm going to introduce the models we're using for physics problem solving, in which we build three multimodal competency across the five-stage approach to solving first-year physics problems. There are three modes in physics, which are visual, symbolic, and verbal. Graphs and diagrams are used to represent physical status and processes visually so that elements and their relationships to each other can be interpreted as a whole system, topologically, and thus in relatively straightforward ways. For example, the free body diagram, which shows the forces applied on some objects, and also a graph which shows the relationship between velocity and time. In the free body diagrams, it's both qualitative and quantitative. it shows some quantity, for example, n, t, f, mg, the forces, and for example, the angle alpha. But on one hand, it's also qualitative because it gives people a relatively rough relationship between those quantities. But on the velocity versus time diagram, it's a very accurate and qualitative diagrams. At each time, the velocity is shown and represented very clearly and accurately. On the other hand, to emphasize the mathematical structure, one would use the symbolic equations. There are various symbolic equations. For example, this equation defines the functional form of a wave. For example, this equation is a derived equation which shows some property, some relationships between the position of the object and its time, given some certain conditions. And for the third equation, it's the famous Newton's second law, which is a law equation that was found from experiment, and it's very fundamental to classical mechanics. And lastly, when people don't want to just focus on abstract structure of the problem, they can also use plain words to describe the concrete situation, the physical situation. For example, this is a problem taken from our material, which talks about a Doctor Who trying to running away from a planet that is going to be exploded. In this problem, we use some numbers for Doctor Who's velocity, its time, and its acceleration. But we also have some other problems that gives no numbers, no exact information. We just add them to comparing a typical human population and the frictional people from Lilliput, where people are very, very short in that kingdom. And we ask them to compare who can jump higher, in which case students have to put more thinking into it because they don't have qualitative information. The quantitative information. They have to come up with their own assumption and thinking. Across the 5 stages, the usage of visual, symbolic, and verbal modes can vary. When students over the 5 stages, from drawing the key elements to using the model to operationalize the solution, finally solve the problem via math, then check and interpret the solution. Visual first take some portion, and when it gets to operationalize the solution using equations, solving the problem, it gets smaller and smaller. But when we come to the checking and interpretation stage, where we might want to use it to interpret the concrete situation, it can be more. It can be the portion can be larger. But for the symbolic, when we're trying to read out the concrete situation in the problem, when we're trying to using reasoning to interpret the problem using models, the symbolic equation usage is not very large. But when we come to the operationalization stage and the solving stage using math stage, the usage of symbolic will be larger and larger. But when we come to the check and interpreted solution stage, we almost don't use symbolic equation because we will focus on what does those number means, what the result tells us in a plain language or in a graph way. The usage of verbal modes is very similar to visual mode. It takes a large portion because people have to read out the problem. Then, because of the usage of math become larger and larger, situation becomes more and more abstract. The usage of verbal parts gets smaller. Then finally, when we have to interpret it and check the solution, it becomes larger again. But why we have this kind of variation of 3 modes in the 5-stage approaches? A very deep reason is because for this 5-stage modes, there are actually 2 phases of thinking or two phases of reasoning. They can divide by this straight line. For the upper 2 stage, it's a physical stage. It connects or describe or thinking connects to the concrete, the physical worlds. But for the lower 3 stages, when it involves modeling, when it involves equations and solving using math, it's an abstract stage. It involves abstract mathematical structure. So for the physical and concrete stage, people would certainly use symbolic equations less and use verbal and visual parts more. But for the abstract and mathematical structure parts, for sure, the symbolic modes will be used more, and the verbal and the visual modes will be used less. In our approach, we will, as we have talked before, we will use scripts as one kind of material for students' analysis, both from the physics side and the linguist side. In the script, we kind of imagine or created 3 characters, which are Ava, Banqiao, and Carol. They have 3 competency correspondingly, which corresponding to the 3 modes in physics. So the symbolic modes corresponds to the quantitative analysis, which Ava had, and the visual modes corresponding to the graphic analysis, which Banqiao had. And the verbal modes correspond to qualitative analysis, for example, the reasoning and so on and so on, which correspond to Carol. Now I would use one example to show how the characters are trying to solve the problem in this 5 stages approach with their competency. And we'll emphasize particularly for different competency what they are pitfall, where their weakness, and if they're to rely on their own competency, it will cause a problem. So this problem we have introduced before. Daku is running a planet with certain speed, and the planet is going to explode in 5 minutes. So basically, you have to run into his own TARDIS, which can bring him away from the planet. And that TARDIS is 330 meters away from him. And the planet will explode in 5 seconds. But because of the air resistance on the planet, Doctor Who starting to deaccelerating with acceleration 2 meters per second. Now the question will be whether the Doctor can get into the TARDIS within 5 minutes and escape the planet before it explodes. At the very beginning, Carol, who is good at qualitative analysis, comes out, read the problems, and draw the key elements of the problem, and then he and Banqiao draw the Doctor Who and TARDIS and label the key information on a graph. And then Banqiao comes out and interpreted the problem using model. He said that because Doctor Who is very small, and we don't care whether his left hand or right hand comes into the TARDIS first, that they will use point mass. Now, because we consider Doctor Who as a point mass, we have tons of equations to solve. And then Ava comes out to pick up the right equation because of the known and unknowns in the problem. And then plugging the numbers into that equation and solved that equation and got 2 roots, the 2 results of the problem. So one is t equals 3 seconds, another one is t equals 10 seconds. In this problem, we're asking whether Dr. Hu can run away before 5 seconds. Now the results tell us 1 is 3, 1 is 10. 1 is smaller than 5, 1 is larger than 10. This is a problem. Why? Because we're trying to figure out whether Dr. Hu can be alive after explosion. Now the results tells us it can either be alive or can either be dead. This problem definitely comes to Carol and Ban Chao, and they can solve this problem or figure out this contradiction with only the mass or the equations Ava provides. So they can dive into the problem, try to interpret the results, and using their reasoning and connect to the concrete physical words. Finally, they figure out that one answer corresponding to the doctor get into the TARDIS and leave. Another one corresponding to Doctor Who deaccelerated and he passed the TARDIS. Finally, when his speed turned to 0, it changes direction and runs back to TARDIS. So that one's longer. They use a diagram to help them to understand what is going on in two situations. And finally, they figure out that only the first one is the correct answer, because when Doctor Who get to the TARDIS, he just get into it and run away. He don't have to pass the TARDIS and come back. So then, with the mode of verbal and the mode of visual, Ban Chao and Carol solve the limitation of the mass modes. Later on, we're trying to, here's an example for a later chapter, which almost the end of the textbook, where we want to be able to see the variation of the growth of development of the characters. So we kind of want to use the competency that is different from the one they had at the very beginning, or they mainly focus on the very beginning. So this problem is basically there's a potential energy corresponding to the potential between two molecules. And the question is asked for the forces of the molecule had or experienced at the minimum potential position. So again, Carol comes out and draw out the key information. And then Ava, although he's good at math, now he's trying to using verbal and graph to analyze the problem. Well, he didn't completely give up math, because she has a very good math ability to look into this equation. They understand it actually corresponds to a spring mass model. Well, he also connects to the real concrete physical problem. Now, Ban Chao comes out. Well, he's good at using visual modes, good at analyze the problem with graphs. He operationalized a solution, basically using binomial expansion to expand the potential around the minimum potential position. And after expansion, he did some calculation using the definition of force and potential energy to compute the force. Finally, Carol comes out to interpret the problem as to check it to see whether it's actually a spring mass model, to see whether it is really a forces corresponding to that potential. So in this example, we show the variation of characters. We show their development of not just focusing on their own competency, but also expanded their skill sets to a wide range. So this is the end of our talk. Thanks for listening, everyone, and we are welcoming any questions, comments, and suggestions.